Hello everyone. Welcome to ASAP seminar, the third ASAP seminar. And today we have Econ Shen and Shan Tan from MIT IBM Watson AI Lab to talk about the stick breaking attention, which is the Eclair 25 paper. That is like a more better version of sigmoid attention and rope-free attention. Stick breaking attention could be imagined as like a new contextualized position encoding. And let's very welcome Econ and Shawn to talk about this new position encoding mechanism.
Hi.
I think there are some echoes.
I cannot hear anything.
Okay, no. Yeah. Hey, mute sound.
Okay.
Anything else, no? Hello? Can you hear us?
Yeah. Perfect.
Okay, great.
Yeah.
Yeah. Okay, good. Sorry. I'm Shawn. I'm here to present stick breaking attention. This was the old title of the paper. So just so that everyone can find the new paper. It's now this after comments from the reviewers, and it's legit comments. And so I'm Shawn. This is work I've done straddling both MIT and Mila, along with Yikang and Song Lin, and supervised by Aaron and Rameshwar. So Song Lin's contribution for this paper is she wrote the initial version of the kernel, where I learned most of my Triton from, and that's how I wrote the scatter emoji and stuff like that. So yeah, that's very very helpful there. Yeah, and so this will be the rough structure of my talk. I'm going to talk about the prior work and why we thought stick breaking made sense for language modeling. Walk through the formulation of stick breaking and its behavior, and then to kind of leave the best for last, I'm going to go through some of the results that we have from training models using stick breaking attention, the length extrapolation, standard benchmarks, and then the interesting stuff for last. I think since this audience probably wants to hear more about those kind of like implementation details, and we can transition to maybe a more interesting discussion. So that's the so as part of the reasons why the reviewers think stick breaking is kind of catch-all, and because there was prior work that the stick mechanism. So there was the neural data router from Robert and Kazuki at Schmidhuber's group. The formulation here was also used in stick breaking formulation, and it has a bidirectional version as well. What they called it was a geometric attention, and that kind of gives a good intuition of how stick breaking works. So if you think about the geometric distribution, what it is effectively if you have a weighted coin with probability P, and you're kind of trying to get a distribution of like how many flips do you have to get to the first hit, and so that gives you kind of like a product of probabilities, 1 minus P to the power of K and P. So whereas in this particular case, if it's stick breaking, you can think of it as every time you flip the coin, the weight changes, and then so that's a beta probability of you getting hits. So that's kind of the construction of stick breaking, and that gives you sort of the intuition of how the stick breaking formulation comes about. This paper proposed overall architecture of the neural data router, which include other contributions, and then they demonstrate its capability on difficult synthetic tasks to show the full capability of neural data router. And then after that, we had a paper that leveraged MOEs for fine-tuning capability. So we're trying to use the features of MOEs to kind of see what how we can train a big model and then specialize it on particular tasks. Further train it by adding more experts. So that was the motivation of the paper. But at the time, we had a hard time, working with softmax attention models. And for whatever reason, on that stack, the stick breaking attention worked very well for training. So that's what we went with. And then so we put that in the paper. And anecdotally, we still find that to be true now. Stick breaking generally gives us fairly stable training curves as compared to softmax attention. And you generally don't want to have like, too spiky training curves in case you're training like a huge model and then you do it for a month and then 1 month in it just spikes up and breaks everything. So paper training curves, good. So a part of the problem with these two papers is that there was a whole bunch of other contributions in them, and then in the reviews of model former, at least for us, there was a recurring question of like why we use stick breaking instead of regular softmax attention, which is legit. Like, I mean, internally for us, it's that we had a problem with the softmax attention at that point. But by this point, we're definitely seeing some benefits of training with stick breaking. And if we want to do anything further with it, we probably should like make an efficient version, try to scale it up, see what else we could, what kind of other downstream effects it has. And so yeah, probably it actually evaluate it properly, and then but that's kind of the reason we wrote this paper. So why did we actually want to use stick breaking? So in one of Yikang's prior work, the stick breaking mechanism was used as a way to model local grammatical structure in language modeling. So if you think about like how my explanation of the geometric distribution and how stick breaking works is effectively you're trying to find the first occurrence of something. So everything is kind of local. You're trying to match the closest occurrence of something else. And this general thing was done in deep learning's RNN era. And so the additional complexity on top of the already linear complexity of RNNs was not favorable for large scale trainings, which is why it generally didn't get adopted. So yeah. But in any case, this idea of finding local structure is still there even in standard transformers. So in this work of I think Alan Chu, he did I think it was called physics of language models. It's been found that the attention hits tend to find construct a grammatical structure especially when in this case where you're trained on a context-free grammar generated sequence. But the behavior it generates, it demonstrates is to attend to the most adjacent non-terminal representation. So there's this idea of the closest matching thing, right? And we think this behavior is useful for modeling natural language, not just at the sentence level, but maybe at the more abstract levels as well. So it's not just like within a sentence you're trying to construct grammar, but maybe there's a higher level rules of how sentences are constructed together to form paragraphs, for example. So the concept of most adjacent isn't naturally modeled by softmax, and we have to rely on the model learning the appropriate correlations between query and keys and the relevant position embeddings. So we wanted to basically embed the thing within the attention mechanism itself. So to kind of hammer home the intuition of how stick breaking works, it has a tendency to assign the highest weight to the most recent logic. So if you look at the diagram here, the top histogram is just basically just the raw logics, and then if you apply softmax, you get the second histogram in blue, and then you get the weights assigned proportionally. So even to the logics further back. But stick breaking, what it will do is it will assign higher weights to the recent logics, and then it downweights later time steps. Especially if an earlier logic has already been kind of quote unquote activated. So maybe another way to kind of reason about these things is if you imagine sigma z ij here to be ones or zeros only. Once you have a 1, anything subsequently will just always be a 0 when you think about the final attention value. So there's this kind of blocking mechanism that happens. Yeah. So the behavior of stick breaking has some downstream effects. So first of all, there's an implicit positioning that's created by doing this. So you can view it as similar in log space. You can view it as a similar mechanism as alibi, which is a learned bias in log space. Jushen's forgetting softmax attention is a more like direct realization of this idea where you learn the actual alibi values, and then secondly, you think intuitively based on everything I've said, this mechanism would have a poor long context capability, let alone length extrapolation. Finally, we find this not to be the case. We can speculate a little bit about why that is later. The form of stick breaking also allows for some conditional computation tricks that could speed up things at inference time. So we're also going to discuss that. And then we find that most of stick breaking attention's implementation is the way you would implement stick breaking in the flash attention style is kind of similar to actual flash attention, with some exceptions that we'll also talk about later. So yeah, for example, the log sigmoids are slow, and then we have some tricks to get around it. Okay, so first the experimental results. We have one small synthetic task, some length extrapolation language modeling task results on 350 million parameter models, and then results on 1B and 3B parameter models. Pre-training on with our Dolomite stack, and then I'll show some results on the standard benchmarks, and then on the ruler benchmark, which is kind of a needle in a haystack type of benchmark. So the first task is the synthetic benchmark, and then the goal is to kind of demonstrate what stick breaking does that softmax does not. We found that stick breaking and softmax both could handle like the standard associative recall task, and this task is basically from Simran's zoology paper that was kind of measuring how well different types of sequence models do on associative recall tasks. And so in the standard associative recall task, there's only one assignment. You're basically assigning values to a variable, and then you're trying to retrieve the value for that variable later in the sequence. In this case, both stick breaking and softmax can do that task. So because to highlight the differences, we try to make a harder version of that. So in this case, we want to do repeated assignments, and then the goal is to retrieve the last assignment of value assignment to the variable. So you can think of this task as kind of similar to a situation you might see in, say, a kind of programming scenario where you're assigning values to variables, and then every time you're querying that variable, you actually just want what the last assignment is. So yeah, so after the initial assignments, you can see in the diagram here, after the initial assignments in blue, all blue pairs are kind of assignments, and then the green pairs are effectively retrievals. So after the initial assignments, the subsequent retrieval phase of the sequence will still be making assignments as you are retrieving them. So for example, B here, you're after assigning 6 to B, later in the sequence, you're trying to retrieve 6 from B, and then you're assigning 1 B again, and then you're again requesting the retrieval for B. So this happens several times in the sequence, and then that's what we're kind of testing it for. So the model is basically trained with a signal on the outputs here as the like kind of normal categorization loss. So the diagram at the bottom shows the attention weights learned by stick breaking, and interestingly, the first layer is showing that there's a very like structured way of doing attention where it associates each value with its variable, and then the second layer looks up the most recent assignment. So as we increase the pairs of these possible variables in the sequence, softmax at the same sized model fails to make the same retrievals. Right. So that's just the kind of synthetic task for stick breaking. And
for this, I want to add something. Can you go back to the previous slides? So this like a multi-query repeated associative recall is actually like a abstract of some real use case in like coding and math. Like for example, in coding, we assign different values to the variable, and we like for standard coding language, we require like the model to like actually record the latest assignment of the value, which is similar to here. And also like for math, like when we do the math, like we also do the same thing, like assign different values to the variable, and then at the end, or like in the next step, we need to retrieve the latest assignment of the value. So I think this is like a reflections of like how softmax and stick breaking will have different behaviors in those kind of like coding and reasoning tasks. Yeah.
Yeah. So then we trained. So in this experiment, we basically trained a 350 million parameter model on Slim Pajama, 2048 context length, and we did this for like a bunch of different position encoding schemes, and try to compare the length extrapolation results. So we test this on increasing context lengths on up to 16K on Wikitext, and most results, most other methods result in a spike in the loss as we increase the context length. So you see here in the x-axis here, it's basically you're doubling the context length every single step. And so the stick breaking basically it steadily improves with more context. So there's more detailed versions of this plot here in the paper, but generally we find that even at this scale, you kind of see this length extrapolation behavior for stick breaking. So we then scaled that up to further 1B and 3B model results, and generally here again, just to emphasize, we're just replacing softmax here with stick breaking, so there's no additional changes to the model, and we find better performance overall on the various benchmarks. Here the differences are not as pronounced. But interestingly, when we look at like MMLU and GSM-8K, in the kind of few short examples, we see some bigger improvements. It's not clear why, but some of these results can vary a bit at this scale. But our current guess is in doing a few short type of task, as in the case of MMLU, this is a kind of a multiple choice task. So being able to attend on the most recent set of multiple choice A, B, C, D options will be helpful instead of being distracted by an earlier ABCD choice that is part of the few shot prompt. Yeah, I mean, this is our current guess of maybe what's happening with stick breaking as opposed to softmax. So yeah, and then using a 1B model, we kind of test it on ruler benchmarks. So what ruler is essentially a suite of needle in a haystack type of tasks. And generally what people do is they kind of fine tune it on a longer, they've done like length extension process on whatever their model is, and then they evaluate ruler on it. So generally the graphs don't look as bad as what we show here, but in this case, we're doing it without further training. So with the original model trained on a 4096 context length, we tested on sequence all the way up to 128K. And these are the kind of like aggregated results. There's again per task plots in the paper, but just generally on average, if you look at the left plot, we're basically outperforming softmax most of the time, and all of the time, and then for the needle in the haystack task, where you're basically trying to retrieve one particular like kind of sequence based on some particular value, we can reliably do that up to 16K, and then the performance falls off a cliff after that. But stick breaking, softmax kind of fails if you just double the context length. Also interestingly, for variable tracking, even at the 4096 context length, softmax can't do that task well, whereas stick breaking is able to do that at 4096, and then again it falls off. So generally, these are like very promising kind of like results for continue using stick breaking as opposed to softmax with rope. Yeah. So yeah, that's basically the general like kind of experiments that we ran, and then the overall results of that. I'm gonna go in more into the implementation details here now, and then yeah, there's some stuff that we've done on top of the paper that I'll share with you. So so I'll talk about some things that are not mentioned in detail in the paper. Yeah.
Maybe we can stop here for the
Okay.
audience to ask some question in the tourist part,
Yeah.
the experiment part.
Right.
I have a question.
Yo.
Yeah. So I see that this deep
I can't hear you clearly.
Sorry.
Can you hear me now?
Yes.
Yeah.
Yes.
I'm guessing you want to ask about this.
Yeah, I wanted to ask about multi-value.
Okay.
Why does it work?
I'm not sure. This I need to. So what multi-value variable tracking? It's one of the ruler benchmarks, right?
Yeah.
I'm not sure. I haven't looked into detail at the outputs of that. What's the question? Maybe I'll look
We
into it.
have plot about the
Yeah. I mean, there's a plot, but like
Yeah, so I see the plot. It is perfect. So my question is just you see this steep breaking attention, it retrieved the nearest stuff, right? But
yes.
when there are multiple values, how do you do that?
Oh, you can do this if you have so if you have multiple values and the number of layers. I guess you can think of it as the more layers you have, the further back you can go.
I'm not familiar enough with the task, but
Yeah.
I suppose those multiple values, they have different contexts. And when you decide which one to pull, you need to considering on the context. Is that the case?
Yeah, the task is that the same key will be associated with many values, and during retrieval, we should retrieve all the values.
I see. So the model can actually do that. It's like Shawn said, if you have multiple layers, the model can start from like retrieving the most recent values. And then once it decides it's already retrieved as future layers, it will mark this one as already retrieved. And then you can actually go through it to get the next value and repeat like this. So I suppose it's like the model may have doing like that.
Okay,
That
makes sense.
You can think of it as like I don't know if this helps or make it more confusing, but here you're assigning you're kind of assigning the variable name to the value in some sense. You can recursively do this multiple times for every instance of that B, let's say for example. And then you can then arrive at all of the outputs that you summarize all the outputs that you need into one embedding and then give the answer. So this is like again a guess of what's happening, but
yeah, okay. Yeah, interesting.
so yeah, like maybe a drawback of this way of doing things to further kind of think about it is like if you have you can't do this for an unlimited number of assignments, right? So that generally the drawback is there with softmax or not. So, because you're trying to encode everything into one embedding.
Will apply to both softmax and
Yeah. That's your question.
Yeah, thanks.
I have a quick question. So for this ruler benchmark, and we can see softmax. So I suppose the training sequence length is like 4K, right?
Yeah.
Yeah, so this is why like Rope has a relatively good performance in 4K, but not that good in other sequence lengths. I was wondering like if so this is more like the expressivity of Rope or it just it's because it cannot extrapolate to longer sequence. What if we train the result the transformer with Rope in on longer sequences? So Max with Rope can solve this problem.
I suspect so for the needle in the haystack task, I think that's been generally demonstrated to be doable. If you train it on longer contexts and then maybe even needle in the haystack type tasks specifically, you can do quite well on the needle in the haystack. I think the ruler paper has like several different models that it tested this. I think variable tracking might be an issue, but I again, I don't know if you just specifically train it on variable tracking tasks, whether you can solve it. Because you're asking about expressivity things, right? So there's a whole thing of like, can it express the answer, the answer? But in this case, it seems like the data needed to make it express that program to do variable tracking is there because stick breaking can learn it, but whereas softmax cannot, or like it has a problem with it. So there may be an issue with expressivity in this particular class of tasks. That's just the intuition I have. Does that answer the question?
Yeah, thank you for your answer.
So I just want to emphasize, I think if people are familiar with the whole wheelbarrow and the state tracking type of things, stick breaking doesn't solve the state tracking issue. kind of emulates it a little bit because it can do the pick the last instance of the whatever was assigned to the variable.
Yeah.
But
Well,
if
for the context, you are referring to the William Maris paper, the illusion of state in state space
yes,
model.
exactly. Yeah.
I see.
Yeah. So we don't get more expressive in that sense. Just in this particular case, we may be able to fudge something because the softmax can't do this particular type of retrieval.
So you are saying like so expressivity wise, steep breaking attention does not have better expressivity than softmax attention. You said that
that's not clear because like I don't know if it's exactly equivalent. But in the state tracking sense, it's kind of both can't do it. Yeah. I don't know if that's makes sense.
Yeah, I'm also unclear like how's the
Okay.
expressivity comparison between the softmax attention and the steep breaking attention.
Yeah. That's a harder question to answer because I think there's many dimensions of expressivity. And the state tracking aspect is one of them. There may be something here where you can kind of say like in a particular case of formal languages where you're trying to retrieve the earliest instance of a particular thing, stick breaking can do it, softmax cannot. So that's kind of what I'm trying to say.
Yeah, okay. And I have one last question. So regarding length extrapolation, what's your intuition that steep breaking attention can extrapolate where softmax attention with rope cannot extrapolate? Do you have can you provide us some intuition about it?
Right. So what I suspect is happening is that steep breaking essentially if you append more things to the end of the sequence, to the beginning of the sequence, sorry. So that means you compute some the A, right, as you go backwards in the from your current token to the start of the sequence. You have a bunch of weights that result in the A. If you append more things to the start of that sequence, it doesn't change the initial weights that you're assigning to it. Whereas in softmax, right, if you extend your context length, a larger logic at the earlier in the context will affect your current attention weights. And so I think that there can be distractors that can happen when you have a very long context length, you accidentally have a higher logic at the start of the sequence, and then you change the attention weight.
In my point, I think there is two aspects of this behavior. So the first one is like for the rope, when you extend to like a longer sequence, you are seeing like on out of distribution position encoding, which give you like unexpected behavior of the like attention. But for stick breaking, there's no such like a unexpected like a value. It's all just based on semantic all the key and value. So you don't really get out of distribution. Another thing is like Shawn said, like you don't really change the distribution of the local, the recent like tokens because of stick breaking. Like this, the probability for stick breaking, it only depends on the what's between I and J. If like let's say J is the query and I is the key. And also like because of this, it doesn't mean that the model only look at the local window, because we already saw in the needle in haystack and also the multi-query like retrieval. We saw that like the model can retrieve the keys from beyond the training sequence length. So the stick breaking is actually has some extra probability that can be assigned to this out of distribution queries or keys. So it's like actually using the extra length. Yeah.
Okay, thank you for your explanation. Yeah, if other audience don't have any questions, so maybe we can move to the next session. Yeah, I think Shawn will be talking about the implementation, right?
Yeah. Actually, before we move on, I want to show those extra experiment results that we have, just to show that the model has actually scaled up, but the performance side still have the. So we train the model up to like a 30 BMOE, which has around 6 billion active parameters. And this give us like, we also have a equivalent softmax baseline. Compared to the previous like 1B and 3B results, we see the consistent performance improvement on like MMU and math and some other tasks. So I just want to show that like this performance-wise stick breaking can also scale to like larger models. It's like not like a we expect a diminishing return like for larger models. That's all.
Yeah, I think one possible concern is that like all of these benchmarks are very short context size. And so for example, MMLU its context size is like pretty small. Yeah, and also for math benchmark. So I was wondering like so aside from the like needle in haystack benchmark from Ruler, so will you be like evaluating on some other commonly used non-sequence benchmark?
I think for that we need to first have a long context or like a context parallel for the stick breaking.
Yeah.
This we are still working on it. We are also open to collaborate with everyone else to continue push this long context aspect of the because like for the 30 BMOE, it's actually take a lot of compute to or like the implementation, we needed like context parallel to actually extend the model.
So
yeah, I see. I see.
To kind of emphasize this, right? Like just even this ruler benchmarks, I ran it on the 1D model. The 3D model starts to complain at the I think 64K or something. So yeah, I couldn't run it easily on that size. Yeah. Okay. So yeah, I'll talk about the some of the implementation details now. So generally the structure is of the kernel is effectively the same. I've been basically trying to learn how to Triton the hard way from Songlin and some like from Mayank here to kind of like learn how to write kernels and stuff like that. So don't expect me this to be the most optimal way to do things, but generally the structure of it sort of follows flash attention. There's a few changes that we must make because of the way stick breaking works. So generally we have a cumulative product in stick breaking where we have to do it in which we'll just do it in log space because that's the only thing that makes sense. And then specifically it's a cumulative sum of a bunch of surplus operations in log space. I've managed to do some manipulation with the log sigmoid here, as you can see. There's some off by one things that's going on here. Everything is working correctly as expected, but you can see some of the derivations in the appendix. And so that there's only one soft plus that we have to compute. The accumulation also, instead of going from left to right, or rather in softmax you can do it in any direction you want. We have to go from right to left here because that's the way being direction is in. And then yeah, the red line on the left that represents the kind of the sum of the soft pluses at the end of the sequence, at the start of the sequence. And then so you can see here that the overall structure is the same as the softmax attention. I've tried to use basically the same diagram as what was used in flash attention. So the colors, the grid there is basically the tiles that you're using to compute the logits and the attention weights. And each color band is a different program or thread block working on its own block of the sequence. So yeah, the overall thing is the same, direction is different. You have to do a bunch of a cumulative sum of soft pluses instead of summing the whole accumulating the max and then computing the log sum x at the end. So for the backward pass, we have to go from left to right and then compute the gradients from the output gradients to QK and V. So in flash attention, the Triton version does a 2-pass summation. So it goes from effectively from left to right and then from top to down towards KV. So the CUDA implementation and the one described in the flash attention paper, they use an atomic add in the Q direction. So when I say direction here, is effectively you can think of it as because Q is on the right side and then K and B is either on the top or bottom, depending on how you want to visualize it. And then those two things kind of come together to form a square, a block in the grid. And the way the Triton implementation of flash attention is done is that there's two passes, one that goes from left to right, and one that goes from top to bottom. So the top to bottom one sums up for the gradients for K and B, and then the left to right one sums up the gradients for Q. In the CUDA version, what they do is they sum up from top to bottom, and then they do atomic adds to Q. So there's only one atomic add per computation of a block in the downward direction. So this is one of the things where softmax can do faster, because your atomic add is only on one block to the Q side. In stick breaking, I can't. I have to do it from left to right, and then the atomic adds has to go towards the K and V direction, which means I have to do an atomic add towards the K and V, which is 2 blocks, and I have to do the weighting for 2 blocks. So there's some overhead there. And I didn't use the atomic add from Triton, so that's a super slow process, and I use some weird locking mechanism that I'll talk about later. So yeah, that's effectively the overall thing about how we implement the state breaking attention. And yeah, so in Triton, some of these things are so straightforward to implement. For one thing, the soft plus computation is really quite slow. And then I ended up with a solution of using the inline ASM to kind of speed up that particular operation. And then I manually implemented like an atomic add to do the summation for K and V. So to start with, I think just talk about soft plus, right? Soft plus is a soft value. So you have this, if you imagine just the rectifier function, it's kind of like a differentiable version of, sorry, let me see. I'll cover that later.
Okay.
It's the next slide. Yeah. So at some point in the positive regime, the soft plus basically becomes X, right? And so you want to be able to kind of exploit that fact. And also the other thing is that if you just let Triton compute X, a number bigger than let's say 15 in our case or whatever, it blows up very quickly. So you want to be able to switch between these two kind of versions of the soft plus computation. And if you do this naive method in Triton, where you use a TL.where, it does both parts of the computation, and then it combines that into one final tile of the output. So I found this to be slow, and it's basically doing a bunch of computations, especially in the case where X is more than 15, where you don't have to compute those things. So what I found is that if I just wrote the relevant PTX that you see there, it computes this at the scalar level, and you get a faster throughput from that. So the downside of doing that is that this kind of makes it hardware specific. So I have a bunch of wrapper code in my implementation to kind of allow it to fall back to Triton if needed. So yeah, that's for soft plus. So yeah, so Han, this is your question, right? Like, how does the manual atomic work? So this is actually, I kind of copied this from the layer norm tutorial implementation in the Triton website. Effectively, what you're doing is you're just doing a busy wait on a atomic, like one atomic integer, and then that's the lock. So you're just waiting there until the lock becomes 0, and then you lock it, and then now there's only one thread that's available, that's possible, that can access the green portion of the code there. And then so in that portion of the code, you can basically do your accumulation, and then you release the lock again. So this only relies on like one scalar in that lock pointer, and then it generally seems faster than a naive atomic add.
Actually, I have a question. So why would this be faster than the naive Triton law? Because I would imagine if a compiler is good enough, they should be able to generate this code for you.
I agree, and I don't really know why.
So basically, you're basically implementing a busy lock yourself using
Yes.
atomic hash. But I feel like if they have the atomic hash intrinsics, even I would imagine the atomic lock itself, the sort of atomic itself is implemented through atomic hash. Although to be fair, I don't
Yeah.
really know how the code gen works behind this.
Yeah, I didn't really look into that because I mean I was staring at the PTX for this and I just no
Interesting.
never again.
And I actually have another question for the
But,
PTX.
yeah. Yeah.
For the PTX instruction. So I think I wasn't sure how to do it in Triton because I'm assuming the PTX instruction requires you knowing the thread block size and the warp size. Do you need
No, yeah. So interestingly, the way the inline, and I think Mayan was telling me that the way inlining works in CUDA is similar. That basically, you're kind of like you see all the dollar signs and all that, right? It's basically going to substitute in register names.
And this is independent of warp or like
Yeah.
so this is what is executed by every lane.
Yes.
So
Yeah.
it's like a scalar operation, scalar input, scalar output. Basically.
I see. Because there's one time I want to do like some like shuffle sync instruction in PTX, but shuffle sync requires knowing how many. You basically know the warp.
Yeah, because the shuffle sync is like intra-thread thing, right? Like that requires two threads to collaborate, basically, or multiple threads. Basically.
I see. So on a per thread, but what if you want to use like vector intrinsics, like whatever you do, like add a two, for example, which requires two lanes to collaborate, whatever.
Yeah,
would that
I'm
make
not
this more
sure.
annoying?
Plays out when
So I think that goes beyond the scope of like what inline element wise ASM is supposed to do, which is the name of it, right? It's like it expects you to do something element wise.
I see.
Yeah, I think the limitation is that like you don't really know what's the grid size and stuff in Python, so it's hard to say like what is exactly happening.
I see. Yeah, because for some point I was thinking about because yeah, I feel like for the atomics I was thinking about like doing some PTX instructions, but then realized I know very little about the compiler code gen behind it.
Yeah, we were discussing the same thing, by the way.
Oh, really? Okay.
Yeah,
Because
we
the
were thinking.
Kala's basically doing what I think what Shawn was writing here, basically do like the atomic has, and then they have it in the HBN, they lock it, and then but yeah, I'm glad I actually figured out how to do it in Triton because I never figured out how to do it.
Yeah, so I didn't know about this. One of our IBM colleagues actually told us that they did that in the layer norm example. So you can take a look at that.
Oh, by the way, we are not sure like this is the most optimal locking mechanism or not. Like, if you look at like, so we were discussing, there is this grid syncing in CUDA, right?
Yeah.
So one possibility is like just taking the grid sync PTX and using it as an inline ASM, but we haven't gotten that far yet.
Yeah. So that comes into all of the things that you were saying, right? Like because when you do that on a particular scalar value, then you don't know what the other threads are doing in the same block, and then it could just bypass the thing entirely, and then it doesn't do what you want. So you don't know what Python is doing behind the scenes as when you do if you don't do like an element wise operation on the inside the element wise ASM.
Oh, by the way, one limitation of this is like the Triton compiler can't inspect the inline ASM.
Yeah.
So any compiler pass before the inline ASM and after the inline ASM will be like optimized as a separate graph in the compiler.
Oh, do they? Interesting. Oh.
Sorry, what's the question?
No, he just said interesting.
Okay, yeah. So
it was interesting.
you are like adding,
that's a good to know. I feel like it's more like a compiler thing. It's like a compiler good enough should be able to figure this out for you.
I agree.
Yeah, but the Triton compiler is like written at a higher level. It wants to be agnostic to like the device architecture. That's the issue.
Yeah. Well, maybe that's even better ways like do MLR pass yourself and then to just like have a new path for the atomic, but then that's like different level.
Yeah, that's one.
Just re-implement Triton entirely, right?
Yeah, that's okay. That's an option as well. Slightly harder though, to be honest. Okay.
Yeah. So
that's for too long, but yeah, please keep going. But
I mean, that was my goal of like sharing all these. Maybe you all have better ideas than I do about how to do these things. But, Yeah, so one of the additional stuff that we can do, which isn't actually fully implemented yet, is that during, like, if, for example, batch one inference, you can skip iterations as you accumulate backwards, right? So the structure of stick breaking self-normalizes to one or less than one in some most cases. So once a given row has summed to one, the rest of the sequence towards the beginning of the sequence, as you sum up from the current token to the start, you don't have to look at that. You can just basically stop. And so the issue here is that when you're doing an entire tile or block, as you see here, like probably during training, you will need the entire block to fulfill the criteria of all summing to one in order to do the early exit, as I'm drawing here in the in this block diagram, the grid diagram here. So even in the batch one case, you also have to kind of ensure that all the hits kind of end early, and then so if it's, as long as one hit has a long-term dependency or it's just not attending to anything, you have still to run the full number of iterations all the way to the beginning of the sequence. So something interesting here is that I played around with implementing this, and I set the threshold to 1, and I'm doing all this in Triton, so I don't know what optimizations are happening in the background. And I set the threshold to 1, right? So this gave me like a 9% speed up on like end to end. So I'm doing this on like the 1B model with 40 layers and everything. I mentioned the number of layers because I think that will come in important later, but it gave me a 9% speed up, which isn't much. And if I aggressively decrease the threshold, so like I let it to sum to less than 1, I can still get reasonable perplexity while still get increasing that speed up by a little bit. So the trend seems to be that the language model actually sort of improves and then gets worse as I go from 1 to 0.5. So I suspect the issue, which is related to Song Lin's earlier question, is that the long context language modeling, the distractions from tokens earlier in the sequence actually make things worse. And then so silencing the earlier, the kind of longer term, further back activations helps to some extent. Yeah.
Also, two more thing I want to add for this is like for now, I think this is just 4K, right?
Yeah.
Like when we keep increasing the model context length, we actually have a good chance to see more improvement with this early exit. Another thing is like if we can find a way to implement this like a interest per head, we may see another improvement on the inference time, because we know like different head in the transformer has different focus. Some of heads is focusing on local or like previous tokens. Some of heads is focusing on more long-term tokens. So if we can like just do this like for each block we only have one head, we have a better chance to early exit for a lot of those different heads. So I think like the potential for this early exiting is like more than just 9%. We need more experiment to verify that.
Yeah, so I bet, I mean, the in the cases I've been testing, it also wasn't exactly batch one. So there's a whole other bunch of things going on. I think at decoding, you might see a better improvement for this. Yeah. Yeah, so it's not just batch one, it's like batch one inference time where I think it will make the biggest difference. So yeah, after this paper was written, we have additional follow-up improvements. Everything that came before, we basically just replaced softmax with attention, and then we see how that did. So we found that some minor changes will help when we modify certain things in transformers. So first of all, using 128 dimensions for the head works better. And we compared this against a standard softmax transformer with like 128 dimensions also. And then generally, because the stick breaking sum of the attention isn't always equals to 1, and it can in fact sometimes be 0, we try to use like a headwise norm to ensure that magnitudes of the heads always stay within a particular range. And then the other thing that we did that helped mitigate that is also to have this remainder bias. So the remainder bias is essentially, it's like an attention sink idea. We assign the remainder of the attention weight to a bias factor for each head. So R is head specific. And then if the attention doesn't attend to anything, then the output of the stick breaking will just be R. And then so it basically has the same idea, right? You're trying to keep the magnitude something rather than just complete being zero. So generally, in this subsequent experiments that we did on a larger scale models, we found that this helps quite.
Yeah, so I just want to add here. So if you look at the 1D experiment results, especially for MMU, like we found this like extra larger learning head size, which is the original head size is 64, which is standard for like 1D model. But after we increased from 64 to 128, we saw the significant improvement on the MMU for smaller models. Now the softmax baseline, which is also using a larger head, which is 28, but the stick breaking is like 37. It's around like 10 points improvement. And after we apply the reminder bias and normalization, this normalization is actually a group norm. So apply on the output of the tension. It's also like normalizing the tension rates. It's just normalizing the output vector. After applying to this, we get like 39, which is like around 11-point improvement on MMU for like without any change of data or like hyperparameters and anything else, just the architecture. So this is quite surprising to us.
I think like so here is like output group normalization, right?
Yes, it's a group norm on the output of the
Yeah.
I think this strategy has been used in like several of the recent work, like differential attention and also for gating transformers. Yeah, I think like many people found that even for softmax attention, like group output normalization is like really helpful.
Yeah, but for now, what we found is like the major improvement on the performance is not from the group norm. Group norm actually stabilize the model training and make it tighter at the length extrapolation, like get longer sequence complexity without training the model. The biggest improvement on performance for the stick breaking is actually from the larger head size and the reminder bias.
I see.
Just a quick question regarding block skipping. Can you do it during training?
Regarding what?
The block.
So yes, you can, but like so that's the thing. Like if you do this during training, okay. So if you imagine in the case of during inference, right? So you're doing decoding. This grid is actually one row. And so you have a less of a problem with trying to make sure that everything in the block is at the same is also already summed to one. So you can do it during training. It's just that I don't know how often you encounter the case where everything in your block will all sum to one. It might actually be very common. And we have some weird plots later that might show this, but yeah, you can. So you can. It's just it may not help much. I mean that's the short answer. Yeah.
So I was just saying that during training, like most of the heads are like very global.
All the okay. So generally, like based on some of the stuff we've seen, I think the lower layers attend to shorter sequences, the shorter context lengths. And then as you go into the middle layers, it attends further back. And then so or certain heads might just switch off and do nothing most of the time. And then so if you have those cases, you don't know, and then you will just keep running all the way to the end of the start.
Oh, okay.
Yeah. So that's I think where the behavior that I've seen when I try to activate this during training time is that at the start of training, so at the beginning of pre-training, model hasn't learned anything. The bias is towards the front. And then so yeah, you get very high throughput, and then you think you're doing great, and then as time goes on, it starts to get worse and worse. And then it kind of converges to what it should be anyway.
Okay. Yeah.
Yeah, so that's really bias. So we've also done some small experiments on length extension to the extent that we can. So what this is essentially, I mean, the standard pipeline of what is done is you pre-train a model, you want to extend it to a longer context length, so you train it, you fine-tune it on data with longer context length. And if you look at the dashed, if you look at the dash lines, those are the language modeling losses for both models. In the case of softmax, we set a rope scaling of 4, and then you can see that the kind of spike in the loss is still kind of faster than what stick breaking does without further modifications or scaling to the softmax to the stick breaking. So this demonstrates part of the problem with the length extension in softmax model. If you want to go to even longer sequences, for example, then what we found is that you have to kind of slowly ramp up the fine tuning. So you go from like 49, you pre-train it on 4096, and then you probably have to go to 16K and then 32K and then 120K gradually. But what we are trying to kind of find out, and then, I mean, it's not really at that scale here in this experiment, is that can we just kind of jump to the end and then try to train it on stick breaking, or how, even with the fine tuning, does it still extrapolate further after that? So in this case, we applied the same fine tuning step to both stick breaking and softmax models, and in both cases we saw like there's slight improvements within the length we extended it to. So in this case, we kind of do additional length long context extension to 16K, and then for both cases of stick breaking and softmax, you kind of get some improvement up to 16K. And then as you extend again beyond 16K, you still get this spike for softmax. Whereas in stick breaking, you see that kind of increased extrapolation for the longer context sequence. So just so that we're clear here, that we know that Wikitext has a very limited context length. So this is actually on the file 10K subset, and then we tested it on the longer context length. So I mean, this bodes well for maybe further length extrapolation. You know, the grand hope is that, you know, we can maybe train it on 256K and then could go to 1 million. But it's a pipe dream. Yeah.
What is the difference between the dashed lines and the solid lines?
The dashed lines are the without further pre-training, without further fine tuning. Sorry.
Okay, so the difference is that whether it is like post-train or not.
Yeah. So yeah.
So like the dash
So by
line is like,
post-training,
let me explain this part. The dash line is basically like we train the model with 4K context length, and we don't do anything else. We directly take the model, and for the softmax, we do a rope scaling, and then we test the perplexity. For stick breaking, we don't do anything at all. We directly test the perplexity. The solid line is like we do the pre-training, get a base model in 4K context length, and then we do a continuous pre-training with like the same data mixture but longer context. Which is 16K context length for like how many steps?
2000.
For like around like 200 billion tokens. Right? It's actually doesn't need that much. I think like 10 billion tokens is what you need. But like always when that want to be consistent. So it's around like 200 B extra tokens on 16K context length. And then we test the perplexity directly as it is after the continued pre-training. That's why you can see like the all those models, like for the solid lines, 16K context length, which is the middle of this graph, is better than the dash line. It's because there is some extra continued training.
Okay.
Yeah, gotcha. Thank you.
Okay, so now we're going into some stuff that we're playing with, and we don't have absolute results yet, but like seems interesting. So we're gonna talk about it. So kind of following Zishan's lead, we kind of like what if we have an additional forget gate on the stick breaking betas, right? And then so essentially, where we originally had a beta that was just a sigmoid, now we have an additional forget gate that's a factor to get the final beta IJ. So sigmoid multiplied by some another sigmoid that's on the key value side, and then that gives you your final beta that you use in your stick breaking. So this essentially allows you to kind of in the cases of what we're trying to do, we're trying to do some kind of conditional computation. And because now the forget gates are only on the KB side, we can effectively throw out a bunch of stuff in the KB cache during inference. And so that was the general goal of trying to do this. So now because you have an F on the KB side, once you predict that the layer and you do a projection in even before you do a projection, you can compute the forget gates. You can already throw away a bunch of time steps, and then that can give you more space in your KB cache, and then you can put even longer context things in. So the question is, or rather the interesting thing is then, what does the forget gate look like after we do the training? So interestingly, so just to explain this weird plot I have here, the higher rows essentially a kind of like a heat map of like where the forget gate is keeping tokens, and then all the way down to the last row. So every row is a different layer in the transformer, and then so when it's closer to 1, it's remembering more. When it's closer to 0, it's forgetting more. 1 is white, 0 is black. So at the initial layers, it's keeping more of the token, the time steps around, and then as you get to the middle layers, it gets more and more sparse, and then it gets denser again at the end of the higher layers when you're trying to predict the next token. So this is an interesting thing that we saw in forget gate. So essentially, I think Zichuan had a question earlier, like how much can we actually do if we had if we did this during test training time, right? So I suspect based on this thing that we did, in the earlier parts of training, the stick breaking attention attends to some very recent time steps, and then so you can do early stopping. You can do kind of that not skipping a lot in the earliest layers. Whereas in the middle layers, because it's mostly 0, it's attending to very long context kind of tokens. You can't easily do that. So there's this weird trade-off like in the middle layers where you can't do the skipping, but then some layers you can. So you end up somewhere around the same in your throughput. So are there any questions about this? I mean, I know this is a confusing plot. It's the only plot we have.
Just a question. Are you plotting all the heads? Yeah.
So each, I'm basically the F here is not head specific. So across the entire token, the time step, it's the same F. So they're all sharing that.
It's very important to use a head specific F, and in that case, what you'll see is most of the heads will be very local.
Okay.
It's quite important. Yeah.
So generally, when doing this, we don't see any drop in performance on like, let's say, language modeling. So this is just this is still quite new. But if we do it a head specific way, then being able to drop some values in KV cache, it becomes harder. But yeah, that's kind of like the downstream thought process, right? Like we're trying to do this so that we can put more stuff in KV cache that's of a longer context, and then so we don't. If you do that at the token time step level, it's easier to kind of organize this thing so that the writing is kind of sparse. Yeah.
Okay. I think we can talk about this more offline.
Yeah, sure. And then so if we do like an additional auxiliary loss on top of sorry, the colors are inverted now. It's because of the way we plot things in. But if we do an additional auxiliary loss on top of the forget gate to kind of like suppress it as during training, we can even go even more sparse. So generally, what I found is that in the middle layers here, 80% of the tokens can be dropped with almost no performance drop in the language modeling case. So that's quite interesting, and that's kind of the thing that we're investigating next week. Yeah. So yeah, just to quickly recap, this is the overall summary of what I've talked about, and yeah, we swap out stick breaking, we swap out softmax for stick breaking, and then we generally get pretty good results, especially on some of the line generalization long context tasks. And then I talk about some of the Triton implementation, and yeah, we're looking to collaborate on future things, including the forget kit and stuff like that. So yeah.
Okay, thank you for your presenting. Now we can take several questions if there are any.
Yeah, just a question about extrapolation. Can you go back to the extrapolation plot in the slides?
Yeah.
Yeah. So are you plotting per token loss, or are you just for example for each yeah.
Yeah, I know what you're asking. So
Yeah.
I think the generally best practice to do this now that we haven't done yet is to kind of plot this per token as the context length increases, and then you average that across the sequences that have that token length. That's what you're asking, right?
Yeah.
Yeah. So no, in this case, we're plotting the as we just increase the context length in LM eval, this is the value we get. So generally, I would say that I understand the concern. The concern is that if that line is plateauing, then effectively what it's doing is it's ignoring a bunch of past context, and then because it's not ignoring that, it's invariant to what's happening there, and then so therefore you get this flat line, which then you can prematurely conclude that it's better. In this case, it's actually going down, but because the rest of the lines are higher, it's can't really see it. But I should do that.
Yeah. So just to mention that you can just train a very small model with a very long context length, and you can already see the like decreasing trend in the loss. So you don't need a lot of compute to do that.
Okay. Yeah. I mean, we can actually I can actually evaluate this on the Trinity model. I did the
Okay.
Yeah.
I have a random thought, like regarding like stick breaking attention versus forgetting transformers. So firstly, you said something like so there's some sparsity pattern. So like forgetting transformers, like it is like gating value. It depends on the input representation only, and in stick breaking attention, the score is based on the double dot between the query and the key. And this is more similar to like query aware like sparsity, right?
Wait, sorry, what's the I think okay, so the thing with the query aware part is that you want to be able to, or like rather the goal of what we're trying to do is to get rid of certain entries in the KV cache so that we can squeeze more things into it, and then so hopefully get longer context in a decoding kind of thing. If you have the queue involved, then you kind of can't throw anything away for the KV, because you need to wait for the queue to decide whether things are sparse or not. That's the issue. But you can go further. So if you look at this thing, right? So now we've basically quote unquote factorized data into two things. One is on the KV side, and then one is an interaction of both. And then you could have potentially another factor that is on the Q side. So if the Q side is 0, what does that mean? That means the entire attention head is doing nothing, and then you can just skip the whole attention compute. So you can actually factorize it into 3 if you wanted. And then you have a whole complicated mess to do, but it's still it's an interesting idea, basically. Yeah. I don't know if that answers your question.
Yeah, I think query aware is like make more sense to me comparing to like the pure forgetting transformers there that for each representation it determines whether this token will be used or not. Yeah, the forgetting gate is like so when the forgetting gate is like set to a very small value. So this so you can drop the KV cache, right, according to your
Yeah,
torque.
So So here F is a multiplying thing, right? So if it's close to zero, that means that the entire beta is going to be zero anyway. You can throw it away. So that's why we can look at the F and then kind of investigate what we don't need and what we.
Okay, interesting. So I have a question for Zhixuan. It is possible to like drop KV cache during forgetting transformers inference?
Yeah, it is possible. It is doable during training as well, but it's
Okay.
just a
Okay. So this like KV cache dropping thing is like depend on the forget gate that is computed based on the input representation only. And so this is like so in the sparse attention literature, I've been recently very interested in sparse attention. And so in many sparse attention pattern, if the KV cache is dropped without like being query aware, like static sparse attention, like in MOBA, like in Quest, they all like query aware sparse attention, and it's very similar to the stick breaking attention, where the value is based on the dot between the query and key, so it is query aware. Yeah, I thought there might be some correlation. Yeah.
Yeah, actually, you can go to the very last figure of my paper, right? Shawn can do that in the appendix.
Oh, you finally have your camera ready.
Yeah,
Wow, so detailed.
the
Where
PDF. Where very last page. The last page. Yeah, this is actually something that I'm implementing, but I'm not implementing KV cache eviction. Yeah, I'm just implementing like rock skipping.
I see.
Second, yeah, the previous one. So like most heads are like super local, so there's a lot of computation that can be skipped potentially.
Right, but your forget gate is cumulative towards the start of the sequence or towards the.
It's just between the queries and keys. Yeah.
Okay.
Yeah.
Yeah. I guess how do you skip that? The issue with softmax is you need to normalize across the entire sequence, right?
Yeah, but if this is like f is extremely close to zero, you can safely skip it. Like it's even below the numerical position. Like
Yeah.
so you can safely skip in this case. And also it should be based on this capital F, not the small f. You need to compute the cumulative. Yeah.
Wait, so F is not the log F is a different thing, right? Log F is the
yeah. So in practice, I use sum of a log of F.
Yeah. I see. Okay. So in the past where we've tried to do this thing with this type of thing with softmax, in other architectures, the issue is that sometimes you have a situation where the F suppresses everything. I mean, equivalent F concept, but like it suppresses everything, and then so the softmax actually renormalizes everything up again. And then so even though F is small, everything could be small, and then you could renormalize it back up again, and then there's the general issue there. You know what I'm saying?
Yeah. But here the forget gate value for the current time set is always 1, so it's fine.
Okay.
Yeah.
Okay.
Yeah, I think I have one concerning about the stick breaking attention is because that in the current long generation one, we can see that in many tasks, the model solve it by maybe copy some task from a very far context. So a potential problem is that if we have maybe some noisy information in the middle context, will the stick breaking because that I need to scan the context from right to left. So I guess maybe sometimes a softmax can directly find the most important information from a far distance, but
right.
the breaking cannot do it with a noisy case. Yeah, noisy case.
So I mean I don't know, like my thought would be that the kind of needle in the haystack is testing for just specifically that, and it seems to do fairly okay. So I'm not really concerned. But yeah, I mean it definitely could be a problem, right? Generally.
Yeah. I think just because that we see many far distance copy pattern in the long generation case nowadays.
Sure. Yeah. But I think I'm not. It's generally at least from our experiments, it's doing better at the needle in the haystack thing. So I'm not like I think that's a setting where what you're saying is important, right? Because you're trying to copy something from long distance away, and then you have this bunch of like distractors in the middle.
Yeah.
So I think that's a relevant setting. I mean, if there's a different one,
I see.
I think this is less an issue because so if you want to copy a sentence from the previous context and then I think like finding the first word is like similar to the so math case, no matter there's like some noise or not, right? And then if you have the first word and the query is like changing every time step, and then you can so because this like query will like selection mechanism, so you can better find the later position and then do the copying operations, right?
Yeah, I'm the query here is involved, so I think that's what you're talking about, right? So I think it can do it, at least based on the experiments we've run. But yeah, I understand the concept because initially we also thought that because of the structure of sleep breaking, it's going to be very short context kind of behavior generally.
Yeah.
Doesn't seem to be the case. So
Yeah, I think I should solve this problem in most scenarios. I'm just concerning about if there are many noisy between. Yeah, so that softmax will also maybe assign some attention to it, but because that it's not from the right to left, so that it can still assign some value from the most important one, but far. But I guess maybe stick breaking, maybe they will sometimes that use the full score in the middle. Yeah, and cannot copy from the start. Yeah.
Yeah, so there's an inherent inductive bias like toward recency token, right?
yeah.
Yeah, I was also wondering, like, so you said, sleep breaking attention could have a very long term, long sequence modeling ability. So which means that it requires like the sigmoid value for like the dot between the core and the keys in the layer token to be like to approach like one, right? So I was wondering like so since like so for sigmoid operation there is some like punctuated gate problem that it is very hard for the sigmoid to learn to be one for all of these position, and then did you actually like draw the attention map and to see like how far it can go for this cumulative sum?
So I don't have that particular thing, but based on the forget gate behavior, what we're seeing is essentially that the initial layers is doing short attention span, and then the middle layers are doing the longer term things where basically the logics for recent things are mostly negative, or like most things are mostly negative logics, and then you get like a one high logic somewhere further back, and it's almost as if like everything kind of summarizes at that particular time step, and then so almost everyone attends to that particular thing in the middle layer, where it's like there's a summarization thing going on, and then as you go further up layers, it's kind of going back to prediction again. So that's our current guess of how it's doing the longer context, I guess, relations and all, and attention and all that.
So I think my question is like for a single layer, if a token in the later position want to attend to the like very beginning token, so it requires the dot between the query vector in the later position and the key vector in the middle of the position. Their inner product to be like their sigmoid value to be very close to one, right? Otherwise, so during this like a steep breaking process, the attention score will be allocated to the middle position, right? So how can the model guarantee? I think this is possible in theory, but I think in practice it's like very hard to make sure that the double dot between the middle positions keys will be all close to one. And I was wondering like if there's some like plot. So you can plot some like distribution,
Right.
like on how many attention score that remains for when increasing the distance.
Yeah, so I don't have that. Essentially, okay, but just to, I think for basically what you're saying, so to attend to the first thing, right? I think you might need 2 layers, especially if you don't use position embeddings. So the first layer basically knows where is the first position, because otherwise you're just independent of all your positioning, right? And then the second layer, you can attend to that first token by making everything. It's actually negative. So if you look at the thing, it's 1 minus the sigmoid, which is then the Z dot product. So that thing will have to be close to 1, which means the sigmoid will have to be close to 0. And then I think that's doable, at least, yeah, based on what we're seeing with the forget gate experiments. So I don't think that's a huge issue for like at the beginning of training, it's definitely going to be somewhat random, but then to learn it so that it's mostly negative and then sometimes positive, I think that's an easier thing to do.
Yeah, so you're indicating that it is totally possible for the model to say, so to let this cumulative product term to be as close as 1 for many steps, right? So yeah, I think my biggest concern is that how to make sure that this cumulative product thing to be close to 1 for all the time, right? It is theoretically possible, but I'm not sure like how it actually performs. I think this is a common concern to steep breaking attention, right? Because you have this cumulative product of the the steep breaking process. Yeah. So you think like so empirically it is not a problem, right? According to your experiment and
yeah. I mean, like practically, we also thought it would be a problem. It didn't turn out to be so. Like we haven't looked into it further, but I mean, generally, I do agree that the I mean, even for the reviewers, right, this seems to be a concern, and then they wanted us to kind of like do some experiments on or like report some statistics on it. The one that I did have was like, interestingly, if I measured like where the expected attention would turn out to be in terms of like relative look back, the stick breaking is actually doing a closer. Okay, so if I take the attention map and then I do an expected value of like which position it's looking back to, the expected value for softmax is actually further back than the stick breaking one. But the stick breaking performance on long contact seems to be longer. So there's this weird averages thing going on that it's hard to explain. At different layers, it's something different is happening. And then so you probably have to break it down at layer wise and then kind of look at it.
I see.
I think the general notion of like the closer attention thing is probably happening in the earlier layers. And then in the later layers, it's basically assigning a bunch of negative numbers everywhere for the Zs. And then in only particular cases where it's important, it becomes a positive number. And then you get this longer term attention. Kind of
yeah. And also, do you think it is possible to have another stick breaking process from the beginning of the token, the sentence, to the current token? So previously, your stick breaking process is like right to left. Then what if you have left to right? Have you ever experimented with it?
Yeah, you can do that. I think there's several ways if you want to go about doing that you can. I think they have a version here where basically, I think they split the heads in half and then say one side is doing the forward thing and one side is doing the backward thing. Yeah.
So I was wondering like why the 2 passes is beneficial. So it reduced like the. So I was wondering like if you have like 2 passes of this stick breaking process, one from left to right and one from right to left, whether it can like to have better like a long sequence ability, because so for the left to right process, you immediately take a look from the very long distance token in the very beginning, right? So
yeah.
I found this is like a
Yeah,
more
yeah.
natural way to guarantee that state breaking attention has some sort of long sequence context ability.
Yeah, maybe. Yeah. You have a different value.
Yeah, so yeah, I think this
It's
is
actually-
interesting.
So okay, so there's some equivalence for state breaking basically from the in some sense there's equivalence from state breaking to the Mamba like gated linear recurrent models. And if you so essentially if you have a gate that is going like G times the previous value plus 1 minus G times the current value, and then you have an update sequence like that, if you expand the whole thing out, you basically get something like state breaking, except now the G is query aware, as you say. So effectively what state breaking is you run a Mamba model from the beginning of the sequence to the current token, and then that final embedding is the output of the sequence. So every queue now has a different Mamba sequence associated with it. If you're running it the other way, then effectively you're running it from the current token all the way to the start of the token, and then that's the summary of the. So there's that interpretation that I think might be interesting also. It might be. So yeah, like I'm not sure if I'm making sense, but there's an equivalence of the at least Mamba to what state breaking is doing, but with a specific queue in place. So now your Mamba is queue specific. So every token now is doing its own Mamba thing. Yeah. So what you're saying is basically running from the current token to the start of the sequence and then have a summarizing vector at the end of it, which is also an interesting idea.
Yeah.
And another potential way should be maybe we can split it into several blocks and formatting some hierarchy, and for each block we can assign it with a score first, and then we gradually assign the score for each token in each block. Yeah, and it can further form a hierarchical, so that I guess in this way that you can make a more robust allocation about this important score to each part. This maybe more design.
So are you thinking of like a NSA kind of idea? Where you like have block? I see.
Maybe more hierarchy, but we can maybe we can compress multiple times, and each maybe we constraint maybe the select one to be in a fixed number, so that we can maybe assign scores to them, so that.
This sounds like a bit of like your previous work.
Yeah.
Okay, are there any other questions? If not, maybe we can end this session, and thank again for Shawn and Econ for presenting the state breaking attention paper.
Yep, no problem.
Okay, so yeah, sorry for the inconvenience in the beginning of this.
No. It was interesting for all of us.
Okay. So I think we have so on Wednesday we have another ASAP seminar this Wednesday. So it will be something similar to state breaking, state tracking. So with delta net, yeah, I invited the delta net with negative eigenvalue author
nice.
to present, and I think they recently also have a interesting paper called delta product, where they perform several gradient descent within a single step. So it could have better expressivity. Yeah, so 2 days later we will have them to present.
Okay.
Okay, yeah, welcome all of you to attend the next ASAP seminar, and see you guys later. Bye.
Thanks everyone.
Thanks for inviting me.